Today our topic is Maxwell thermodynamics relation. This topic has become many times long question in your past papers, and so you can derive any two relations if the two relations are required, and if three are required you must derive three Maxwell relations. As you know the equation where we know the change in internal energy is equal to the differential of the work plus differential of the heat. Work is equal to the minus PdV. Why is this so? Because work is about the change in the pressure and increase and decrease of the volume when a gas is present in the container. So we can say that the work is about increase or decrease in the volume by the change in the factor of pressure. So here the work is given as minus PdV. And when we talk about the heat causes the change in the entropy, and it is caused by the temperature, means that entropy changes by the increase or decrease of the temperature. This is all about the heat effects. So when we write the exactly formulas of the work given here, minus PdV and the differential Q, then it becomes plus TdS. Enthalpy is noun like enthalpy H is equal to E plus PV. Enthalpy means is represented by H. It is equal to the entropy plus pressure into volume. Differentiating the above equation, the equation is differentiated on both sides, so we get this. Differential is simple here on the left side, but on the right side we have to differentiate different factors. First, the differential of the entropy becomes simple, and the differential of the PV is taken turn by turn. Means that first we will take the differential of the volume, so it becomes P as simple as it was pressure and differential of volume. Next time the V is taken as simple and the differential of potential is taken. Means that the turn by turn differential is given. First is given to the volume, second is given to the pressure. Putting the value of dE, this one value of dE that we have derived here, this one, right? This one value of dE that we have derived here, we will put this value in this equation. By putting the value of dE in this equation in the place of dE, we get the equation in this form, and we can see that here some things are cutting. What things are cancelling out? Minus PdV is cancelling out by plus PdV. The equation remains in this form, means that the change in the enthalpy is equal to TdS plus VdP. Now let's talk about Helmholtz energy can be defined how. Helmholtz energy formula is equal to A is equal to E minus Ts. What is A here? A is here as the Arrhenius constant. E is internal energy. Minus Ts is representing a factor where the change in entropy is depending upon the temperature. So differentiating the both equations, it become very easy, because we have done in the case of the enthalpy before this. The entropy change, the differential of the Arrhenius is equal to the differential of the internal energy minus the first differential is given to the entropy, the second differential is given to the temperature. So the equation appear in this form. So by putting the value of dE that we have derived and that we have done in the previous discussion also, where we will put the value of dE, the equation appear in this form. What was the dE value? dE value was minus PdV plus TdS. So by putting the value of dE minus PdV plus TdS, the equation become in this form. What the things are cancelling out? If we notice, the things that are cancelling out is the plus TdS and minus TdS. So the result obtained is minus PdV minus SdT. This is all about the Helmholtz energy. And when we talk about the Gibbs free energy formula is equal to F is equal to H minus Ts, where Gibbs free energy is represented by F. H is equal to the enthalpy, as you know, and minus Th is the factor where the entropy change depends upon the temperature. When we apply the differential on both sides, the differential method is equally same. So putting the value, now we do not have in the equation dE to put its value, but we have dH value, so we will put here the dH value rather than dE value. What was the dH value? It was TdS plus VdP. By putting this value, the equation appear in this form. What the factors are cancelling out, you can find it out. the two factors are cancelling out. One is TDS, other is minus TDS. So the remaining equation is DF is equal to VDP minus SDT. This is all about the three relations that you have studied, or four. The number one was about the internal energy, then you studied about the enthalpy, then at third Helmholtz energy, and at the last Gibbs free energy. So we are going to study or explain these four phenomena in the further derivation. This is not the end of the question. What to do now? We have come to know that internal energy, enthalpy, Helmholtz constant, and the Gibbs free energy are state functions, and these have expressed in the derived equation in the previous segments. Now we are going to talk about the obtained equation. The obtained equation of the first equation, that was internal energy, was this. And from this equation we are getting to know that this equation is showing that E is a function of the volume and the entropy. So if we want to change this left side factor dE, internal energy, into this form, how is this possible? We can do this by keeping remember that internal energy is depending upon the volume and the entropy. So we will say that differential E divided by differential V. If we are dividing differential V by ourselves, then it means that we have to multiply this differential V as well. So the same we are dividing it and is multiplying, and the S is taken as constant because we are taking here differential of the volume at the constant entropy. And same here, when we are taking the differential E, this differential E, and we are dividing the entropy differential, we should multiply the entropy differential as well. So we are multiplying as well according to the rule of mathematics. So we know that when we multiply something, then we divide something. If we add something by ourselves, then we negate something ourselves. So here we are dividing the entropy differential, so we should multiply as well. So simply we are multiplying here, and the volume is taken as a constant because we are taking the differential of the entropy at one time. The one differential is taken and the other factor is taken as the constant, that is shown by the bracket outside. So this was all about the changed or the derived form of this simple dE. All about the left side, and the right side is copied in the same way. Comparing the coefficient of dV and ds, if we compare the coefficient del E divided by del V is equal to, we suppose not, we know that this is equal to pressure. Always this become equal to pressure. And if we talk about the entropy divided internal energy divided by entropy at the constant volume, when these three factors are studied, mean that change in the internal energy with respect to the change in the entropy at the constant volume, this always equal to temperature. So similarly we will talk about the next equation that we gathered about in the previous stages. It was the change in the enthalpy, that is equal to TDS plus VDP. This equation is telling us that the change in the enthalpy is depending upon the factor entropy and the pressure. It means that the enthalpy is a function of the entropy and the pressure. So if we want to change the left side value from the simple E into the derived form, what the derived form into the noun form, that we are knowing that this is depending upon the factor of the entropy and the pressure. So we want to write the equation in that way. So we will take this differential of the enthalpy and divided by the entropy, multiplied with the entropy, and by taking the pressure second functional factor, second depending factor constant. So if we take the differential multiplication of the pressure and divide it also, so by taking the other factor constant, as means that when we are dividing and multiplying one factor, we are keeping the other factor constant. So the left become a side of the enthalpy change appear in this form, and the right side remains the same. We will copy it on the right side. Okay, now in the equation we gathered del H divided by delta S at the constant pressure. When the change in the enthalpy with respect to the change in the entropy occurs at the constant pressure, this is equal to temperature. When change in enthalpy with a change in pressure occurs at the constant entropy, then it equals to volume. So these are the factors that we are writing here to be used later on. Okay? In the previous stage we have also done this. Now let's talk about here, where we have come to know that here the change in the Helmholtz factor came in this form: dA is equal to minus pdv minus sdt. So since a is the factor, this equation is telling that what the factors are changing here is the changing factor is the volume and the other is the temperature. So it means that the a is a factor of the volume and the temperature. So we will change the left side, means that a simple dA factor in this form by using the functional factors. How we will do this? We will take the dA divided by the dV first. So if we are dividing the dV by ourselves, we should multiply, and by taking the other factor constant. What is the other factor? Temperature is the other factor. So in the same way we will take here the differential of the Helmholtz constant with the differential of the temperature by dividing with the differential of temperature, so multiplying it as well, and taking the other factor constant. What is the other factor here? It is volume. So the right side remains the exactly same, that is copied in the same way. So if we take these differential factors, so when the change in the Helmholtz is studied with relation to the change in the volume at the constant temperature, it is equal to the pressure. And when we talk about the change in the entropy with respect to the temperature at the constant volume, then it is equal to the minus entropy. That was equal to minus pressure, and that was equal to the minus entropy. Okay, now let's talk about the change in the Gibbs free energy. That Gibbs free energy change is given in this form, where del F is equal to the VdP minus STT. Since F is a factor of the pressure and temperature, so we will change the left side equation of the Gibbs free energy in this way: differential of the free energy divided by the differential of the pressure by taking the other factor constant, that is temperature. And when we are differentiating or when we are dividing the differential of pressure, we should multiply it as well. So if we are taking the again we are taking the Gibbs free energy, dividing it with the differential of temperature, so it will be multiplied as in the same way, and the factor is taken as the constant, that is the pressure. So on the right side the equation remains the same, it is copied in the same way. So when we take the differential factors, that is the differential F over differential P at the constant temperature, it is always equal to volume. So if we study about the change in the Gibbs free energy with the change in the temperature at the constant volume, pressure at the constant pressure, change in the Gibbs free energy and with the change in the temperature at the constant pressure, it is equal to minus entropy. So as we know that modification, now we are going to modify the equation that we have obtained in the segment 1 2 3 4. I have numbered in the picture that form of the derivation, the thing that we obtained in the first form of derivation, in the first segment of the derivation, that was from the dE is equal to minus pdv plus tds. So we modified the equation and obtained it in the other form. There we get to know that the differential E over differential V's factor at the constant entropy was equal to the minus P, and we also have assumed that the change in the entropy divided by the change in the internal energy divided by the change in entropy at the constant volume is equal to the temperature. So by taking and keeping remember that assumed and that certified that specialized factors, we will get to know the modifications of these equations. So when we write the first determinant, the first assumed factor, then we are noticing here that the entropy is taken as a constant. So we will here to take the modification, we will take the differential divided by differential entropy, and we are saying here that this differential of internal energy divided by differential of entropy at the constant volume is given. So to take the modification, we are putting the differential divided by the differential of volume by ourselves. So using this equation in the previous segment number 1, we have find it out that this factor is equal to minus pressure and this factor is equal to T. So simply the equation become in this form. Okay, when we talk about this equation that is obtained, now next to be determined is the second thing, that is the enthalpy. This is all about I was talking about. This is your entropy enthalpy change. On the left side of the equation of the segment B, you obtained this form. On the right side, it was another factor that is not our concern in this portion, so we are neglecting it and we are focusing on the left side equation, so that we obtained in the second segment. So this is the equation that is obtained, and when we modify, when we see it from these two factors are the differential factors, and if we want to change or modify the equation, we will take these two differential. On the one is the right side, one on the right and left side, simple. So we are looking here that this P is the constant, so differentiate or modify the aspects of this equation, we will include by ourselves the differential divided by differential of P, because here P was constant, so we are adding by ourselves the differential of the pressure to change the aspect of the equation. Here we are saying that here the entropy is a constant, so change the aspect of the or modify the equation, so we will include by ourselves the differential divided by differential entropy. So by putting the value of delta H, mean the enthalpy change divided by the change in the entropy at the constant pressure, that was assumed to be equal T in the segment 2, and this factor was assumed to be equal to volume. That was how we were assuming the factors. We are putting it here, so the equation become in this form. Here is talked about the Helmholtz constant. The left side equation appeared in this form. Here the differential vectors are these two. When we take one of the right side, one on the left side, so when we observe the equation, we get to know that the temperature is here on the left side constant, so we will include by ourselves the differential divided by differential of temperature on the left side, and we can see on the right side volume is taken as the constant, so we will include by ourselves the differential divided by differential of volume. So when we put the value of differential A divided by differential V at the constant temperature, we have assumed this in the segment C is equal to B minus P, and this portion is to be equal to the minus S in the segment third. This was all about the segment. I have mentioned in the picture as well, that is 1 2 3. You should also mention there, otherwise it will cause the confusion, because the derivations are used and the points or factors that are assumed are used again in the derivation. So make it easy and mention the points. So simply by noticing all of these things, we get to know that the equation appear in this form, and when we multiply these factor, it become differential minus p differential p minus differential p over delta T. So it was about minus differential of pressure divided by delta T is equal to the minus differential S over differential V. So when we talk about the things here, that is here that was about the Helmholtz factor change. So we have put in the value and gained this form. So now when we talk about another factor, that is about the Gibbs free energy. On the left side in this fourth segment, we obtained this form, and we are here observing that these two factors are differential. We will take one on the left side, one on the right side. So when we look at our left side, we get to know that temperature is constant, so we will put in the differential divided by differential temperature by ourselves on the left side, and pressure is constant on the right side, so we will include the differential divided by differential pressure by ourselves on the right side. So when we have assumed these factors 2b is equal to v, this factor is equal to the minus s in the segment 4 of the previous segment derivation. So by putting these factors in the equation appear in this way, and we are finding here that differential volume divided by differential temperature at the constant pressure is equal to the minus differential S over differential P at constant volume. Why we are deriving all these factors, we will get to know in this paragraph, where it is said that where the differential V, differential T at the constant pressure is a measurable quantity, and the one side of the quantity is not measurable. So this was all about the Maxwell relation, that was mathematical relation, theoretical about the heat, and this relation is used for the determination of quantities which are not necessarily measurable, by taking the use of the quantities or the factors that are measurable. For example, if we want to measure this segment that is unmeasurable, how we can measure? We can measure it by measuring this factor that is measurable. That is how, that was why we are equalizing the factor, as we have done it here also, right? So in the all four segments, one part was the unmeasurable, one part was the measurable. So it was all about the make possible to measure the impossible measurements by taking the use of the measurable sides, because one side is right, one is left, one is unmeasurable, one is measurable, and one is unmeasurable. So if we want to know the value of the unmeasurable factor, so we can determine it by measuring the value of the measurable quantity. This was all about the application of the Maxwell relations. So this is your long question that is highly important, you must notice it nicely. Okay.